When you first imagine looking inside an atom, your mind almost automatically reaches for familiar images. Tiny balls, little orbits, something solid and mechanical, just very small. That instinct is completely natural and completely wrong. This is exactly where Richard Feynman insisted we slow down and admit something uncomfortable. The atom does not contain objects in the way our intuition demands. It contains possibilities. This is not a poetic statement. It's a precise one. Inside an atom, you do not find electrons behaving like miniature particles, tracing neat paths. You find wave-like descriptions, probability amplitudes, mathematical structures that tell you what could happen if an interaction occurs. The atom does not commit to a single story until it is forced to. And that alone should make us pause, because it means the most basic building blocks of reality are not built out of things at all. Feynman was blunt about this. If you try to imagine what an electron is doing inside an atom when no one is looking, you will fail, not because you're not clever enough, but because the question itself is flawed. The atom is not hiding a detailed picture from you. There is no picture there to be uncovered. There is only a set of rules that determine what outcomes are allowed when the atom interacts with something else. This overturns a deep psychological habit. We equate understanding with visualization. If we can picture something clearly, we feel we've grasped it. But atoms punish that instinct. The more you try to force them into familiar shapes, the more confused you become. Real understanding, Feynman argued, begins when you stop demanding that nature fit your mental comfort. At the atomic level, asking what is it doing right now is often meaningless. The atom is not in the business of performing for an audience. It exists as a structured uncertainty, a constrained field of potential actions. Only when you interact, when you measure, collide, absorb, emit, does one of those possibilities become real. And here's the unsettling part. This is not a limitation of measurement technology. It's not that we can't yet see what's really going on. The theory works precisely because it does not assume hidden certainty underneath. The probabilities are not placeholders for ignorance. They are the core description. That realization forces a philosophical shift. If matter itself is not made of solid certainties, then solidity is something that emerges, not something that exists at the foundation. The table you're sitting at feels solid because trillions of atomic interactions average out into stability. But zoom in far enough, and that solidity dissolves into statistical behavior. Feynman loved this point because it separates seriousness from arrogance. You can take physics seriously without pretending it gives you a comforting picture of reality. Nature does not owe us intuition. It owes us consistency, and it delivers that with brutal honesty. There's also a quiet lesson here about how we think in everyday life. We often demand certainty before we act. We want clear identities, fixed plans, definite outcomes. But the atom shows us that stability does not require rigidity. It emerges from flexibility governed by rules. Possibility, when properly constrained, is not chaos, it's structure. Atoms exist because electrons are not pinned down. If they were, matter would collapse. The very fuzziness that makes us uneasy is what allows the world to exist at all. Uncertainty is not a flaw in reality, it's a feature that makes reality possible. So, when you look inside an atom and feel your intuition fail, don't treat that as defeat. Treat it as an invitation. The universe is showing you that the deepest truths are not objects you can hold in your hand, but patterns you can learn to respect. And once you accept that, you stop trying to force reality to be simple and start learning how it actually works. Once you accept that atoms are made of possibility rather than solid little objects, the next realization follows almost immediately. And it's even more unsettling. Looking is not a neutral act. Inside the atom, observation does not simply reveal what is already there. It changes what the atom is allowed to be. This was one of the points Richard Feynman returned to again and again, because it attacks a belief so deeply ingrained we rarely notice it, that reality exists fully formed, and we are just passive spectators. At the atomic level, that belief collapses. When you measure an atom, you are not opening a curtain to see a pre-written scene. You are stepping onto the stage. The interaction itself becomes part of the outcome. Before measurement, the atom exists in a range of possible states, all consistent with the rules of physics. After measurement, only one of those possibilities survives. The rest are not hidden somewhere. They are gone. This is not because the atom is fragile or confused. It's because the concept of a definite property often does not exist before interaction. Asking what was the electron doing before we looked sounds reasonable, but it assumes the electron had a single, well-defined behavior waiting to be discovered. Feynman made it clear that this assumption is the mistake. Nature does not work that way. The mathematics doesn't describe observation as uncovering truth. It describes it as enforcing a condition. Measurement is a constraint placed on the system. You ask a question, and the atom must answer, but it is not obligated to have prepared that answer in advance. This deeply challenges our psychological comfort zone. We like to think that knowledge is cumulative and independent of the knower, that facts are facts whether or not anyone checks. But atomic physics teaches us that some facts only come into existence when interaction happens. Reality is not shy. It is conditional. Feynman resisted turning this into mysticism. He didn't claim that consciousness creates reality or that the mind has magical powers. What matters is not awareness, but physical interaction. A detector, a photon, a collision, these are enough. Observation is not about human attention, it's about participation. And that distinction matters, because it removes the ego from the story while keeping the lesson intact. The universe doesn't care who looks. It cares that something interacts, and when it does, the system must commit. There's a philosophical weight to this that extends far beyond atoms. We often believe our lives are about discovering who we already are, uncovering a fixed identity hidden somewhere inside us. But the atomic lesson suggests a different model. Identity emerges through interaction, through choices, constraints, and responses to the world. You are not a finished object waiting to be revealed. You are a set of possibilities being narrowed over time. Inside the atom, stability comes from this process. Without interaction, there is no definition. Without definition, there is no structure. Observation doesn't destroy reality, it gives it shape. Feynman found this both humbling and liberating. Humbling, because it reminds us that our common sense picture of the world is not fundamental. Liberating, because it means the universe is not frozen into inevitability. Outcomes are not decided until they must be. So the next time you hear that looking changes the result, don't hear it as a limitation or a flaw. Hear it as a description of how reality actually functions. The world is not something you merely witness. It is something you participate in shaping, one interaction at a time. And if that's true at the level of atoms, then perhaps the most important question is not what is already there, but what kind of interaction are you creating right now? If observation forces an atom to choose, the next strange realization is that the path it takes to get there is nothing like the clean, orderly trajectories we imagine from everyday life. At the atomic scale, nature does not behave like a tiny version of the visible world. Particles do not travel along neat lines from point A to point B. Instead, they explore every possible path simultaneously, including ones that seem absurd, inefficient, or outright impossible from a classical point of view. This idea unsettled even seasoned physicists, and yet Richard Feynman showed that it wasn't philosophical speculation, it was the most accurate description we have. When light moves from one place to another, it doesn't decide on the shortest or fastest route in advance. According to the quantum description, it samples all conceivable routes, looping, detouring, even momentarily going backward in time in a mathematical sense. What we observe as the final outcome is the result of all those possibilities interfering with one another, canceling out where they don't work, and reinforcing where they do. The path we see is not chosen because it is simple, but because it survives the competition of alternatives. This is deeply counterintuitive because our brains evolved to track solid objects with predictable motion. We rely on cause and effect sequences that feel linear and intuitive. But at the atomic level, causality is distributed. The outcome is not produced by a single history, but by the balance of many histories that never become directly visible. Feynman liked this idea because it stripped away the illusion that nature owes us simplicity. The universe is not obligated to behave in ways that feel comfortable to human intuition. It behaves in ways that are consistent, and consistency, not familiarity, is the real test of truth. There's a psychological lesson buried in this. We often assume that progress, whether in science, life, or thought, comes from following a single correct path. We're taught to optimize, streamline, eliminate detours. But the atomic world suggests something different. Outcomes emerge from exploration, not certainty. From many attempts, not one guaranteed route. At the quantum level, inefficiency is not wasteful, it's essential. Without the contribution of all those alternative paths, there would be no stable result at all. The clarity we observe at the end is made possible by the chaos underneath. This reframes how we think about uncertainty. We tend to treat uncertainty as ignorance, as a temporary lack of information that should be eliminated as quickly as possible. But in fundamental physics, uncertainty is not a bug. It's a feature. It's what allows systems to adapt, stabilize, and exist in the first place. Feynman was careful to point out that we don't get to pick which interpretation feels nicest. Nature doesn't negotiate. The equations work, whether we like them or not, and when we follow them honestly, they lead us to a universe where certainty is rare, but reliability still exists. The predictions are accurate, even if the underlying story defies common sense. That combination, unpredictable processes producing dependable results, is something we encounter everywhere, once we know how to look. Creativity, learning, discovery, even personal growth all follow similar patterns. You try many paths. Most go nowhere. A few interfere constructively. And suddenly, something coherent appears. Inside the atom, order is not imposed from above. It emerges from below, from the interaction of countless possibilities. That's a powerful shift in perspective. It tells us that complexity does not need a central planner, and that meaning does not require a single predetermined route. So when the atomic world seems strange, it's not because it's broken or illogical. It's because it's honest. It shows us a reality where exploration comes first and explanation comes later. And if that's how nature builds something, as precise as the universe, then perhaps the wisest thing we can do is stop demanding certainty at the beginning and start trusting the process of thoughtful exploration to reveal what actually works once you accept that atoms don't follow clean paths and don't possess definite properties until interaction. The next unsettling realization arrives almost automatically at the deepest level. Reality is built on probabilities, not certainties. This is usually where people start to get uncomfortable, because probability sounds like ignorance, like we just don't know enough yet. But that's not what's going on here. The probability isn't in our heads, it's in nature itself. When we look inside an atom, we don't find little objects with hidden labels waiting to be read. We find likelihoods. We can calculate precisely the chance that an electron will appear in a certain place with a certain energy or moving in a certain way, but we cannot demand a single guaranteed outcome in advance. And the remarkable thing is that this fuzziness does not come from sloppy experiments or weak instruments. It remains even when the mathematics is exact and the measurements are flawless. Richard Feynman was very clear about this point. If you think quantum uncertainty is just a temporary problem that will disappear when we figure things out, you're missing the message. The theory is not unfinished. It is finished, and it tells us that nature itself does not assign definite answers until the moment of interaction. The probabilities are the final story, not a placeholder. That forced a shift in how we think about what it means for something to be real. In everyday life, we assume reality means something has a specific state, whether or not we're looking. A chair is where it is. A clock is ticking at a certain speed. A stone is either moving or not. But at the atomic level, those assumptions collapse. Reality becomes conditional. It depends on how the system is allowed to interact with the rest of the universe. This is not philosophical wordplay, it's experimentally verified. If you design an experiment that asks one kind of question, the atom gives one kind of answer. If you ask a different, incompatible question, you get a different answer. And there is no deeper layer underneath that reconciles them both at once. Nature does not store a secret answer key. It responds to the question asked. Psychologically, this is hard to swallow because we crave solid ground. We want to believe that beneath uncertainty there is a fixed truth we could access if only we were clever enough. Quantum physics tells us that this desire may be misplaced. The universe is not withholding certainty out of spite. It simply doesn't operate that way. What's fascinating is that this probabilistic foundation does not lead to chaos. On the contrary, it produces astonishing stability. Atoms behave consistently. Chemistry works. electronics function. The world doesn't dissolve into randomness. Larg. E-scale order emerges from microscopic uncertainty with incredible reliability. That tells us something profound. Certainty is not a requirement for order. There's a lesson here that reaches far beyond physics. We often postpone action in our own lives because we want guarantees. We want to know the outcome before we begin. But the atomic world suggests that progress doesn't come from certainty. It comes from well-structured uncertainty, from acting with good rules, clear constraints, and an openness to multiple outcomes. Feynman admired this aspect of nature because it was honest. No false promises, no comforting illusions, just a system that works, even if it refuses to give us the kind of certainty we emotionally prefer. The equations don't say, here's what must happen. They say, here's what can happen, and here's how likely each possibility is. And that's enough. It's enough to build stars' life and consciousness. It's enough to make predictions more accurate than any classical theory ever achieved, which should make us pause and reconsider how much certainty we really need to move forward intelligently. Inside the atom, probability is not weakness. It's the engine of reality. And once you see that, uncertainty stops looking like a flaw to be eliminated and starts looking like a space where new possibilities are allowed to exist. If the universe itself advances without guarantees, then perhaps the most rational thing we can do is stop waiting for perfect certainty and start acting thoughtfully within the probabilities we already have. As we move deeper into this strange atomic world, another idea quietly overturns one of our most trusted habits of thought: the belief that understanding means being able to picture something. We are trained from childhood to think that if we can draw it, imagine it, or visualize it clearly, then we understand it. And if we can't, then something is wrong either with the explanation or with us. At the atomic scale, this instinct becomes a trap. Richard Feynman was famously blunt about this. He warned people not to confuse a mental picture with understanding. In fact, he went further and said that if you think you understand quantum mechanics because you can imagine it, you probably don't understand it at all. That sounds provocative, but it's deeply practical. Atoms do not behave in ways that map cleanly onto our everyday visual intuition, because our intuition evolved to handle rocks, animals, and falling objects, not electrons and wave functions. When we ask, what is an electron really doing, we often expect an answer in the form of a tiny object moving through space. But that question itself is flawed. The mathematics tells us what outcomes to expect when we interact with the electron, not what picture we should hold in our heads when we're not looking. The theory works spectacularly well without giving us a movie to watch. This is where many people feel cheated. They want the comfort of a story, a clear narrative of what's happening behind the scenes. But nature does not owe us a story that fits our imagination. It only owes us consistency between prediction and observation, and it delivers that with astonishing precision. What's psychologically interesting is how strongly we resist this idea. We keep trying to force atoms into familiar shapes. Little balls, tiny waves, miniature solar systems. Each metaphor works briefly, then breaks down. The problem isn't that we haven't found the right picture yet. The problem is assuming that a picture is required at all. Feynman emphasized that physics is not about how nature looks, but about what nature does. If you can calculate what will happen, and the calculation agrees with experiment, then you understand the phenomenon at the deepest level science allows. The demand for visualization is an extra human preference, not a scientific necessity. This realization has philosophical weight. It suggests that reality is not obligated to be intuitively accessible. The universe is under no obligation to make sense to the primate brain that evolved on the African savanna. And yet, through abstract reasoning and mathematics, that same brain can still uncover laws that govern the entire cosmos. That's not a weakness of human thought. It's one of its greatest achievements. There's also a humbling lesson here. At the atomic level, we must accept that some truths are accessible only through structure, logic, and experiment, not through imagery. That requires intellectual maturity. It means letting go of the need for comfort and replacing it with respect for evidence. This idea doesn't stay confined to physics. In life, we often reject valid insights simply because we can't see them clearly yet. We distrust processes that don't offer immediate intuition. We hesitate when outcomes aren't easily imagined. But the atomic world shows us that reality can be reliable, predictable, and profoundly real even when it refuses to be visualized. Understanding, then, is not about building a mental picture that feels good. It's about knowing which questions are meaningful, which predictions are testable, and which expectations we must abandon. The moment you stop demanding that nature explain itself in familiar terms, you actually begin to understand it more deeply. Atoms don't make sense because they aren't designed to. They work. And that distinction between what feels understandable and what actually is may be one of the most important lessons science has ever taught us. If you're willing to let go of the need to picture everything, you gain something far more powerful, the ability to understand a universe that operates beyond intuition and still invites you to explore it. As we reach the deepest layer of this discussion, something subtle but transformative comes into focus. When you look inside an atom long enough, the strangest discovery is not about particles or probabilities, it's about us, about how the act of looking changes the very questions we're allowed to ask. At the atomic scale, nature stops behaving like a passive object waiting to be observed and starts acting like a participant in the experiment itself. That idea feels unsettling because it collides with a deeply rooted belief that reality exists fully formed, independent of observation, and our job is simply to uncover it. Richard Feynman was careful here. He didn't claim that human consciousness magically creates reality, and he rejected mystical interpretations. But he was relentless in pointing out something equally disturbing: the outcomes we measure at the atomic level cannot be separated from the way we choose to measure them. Not philosophically, but operationally. The setup of the experiment determines the kind of answers nature is willing to give. This forces a shift in how we think about truth. Atoms don't reveal a single, hidden story underneath everything. Instead, they present a structured set of possibilities, and our interaction selects which aspect becomes real in that moment. That doesn't mean reality is subjective and a loose, anything goes sense. It means reality is conditional. The rules are strict, mathematical, and unforgiving, but they only apply within the context of a specific interaction. Psychologically, this is hard to accept because we crave certainty that exists independently of us. We want to believe there is a final picture, a definitive answer waiting behind the curtain. Atomic physics suggests something more subtle. What exists is not a picture, but a framework of relationships. The electron is not a thing with hidden properties waiting to be discovered. It is a system that responds lawfully when questioned in a particular way. This has profound implications beyond physics. It challenges the idea that knowledge is about passively receiving information. Instead, knowledge becomes something participatory. The questions you ask matter. The tools you use matter. The assumptions you bring with you shape what you are capable of seeing. Feynman often emphasized intellectual honesty here. You don't get to pretend you're outside the system, looking in from a neutral vantage point. In science and in life, you are always part of the process. That doesn't make truth arbitrary. It makes responsibility unavoidable. You must take ownership of how you frame problems, how you test ideas, and how you interpret results. At the atomic level, this destroys the fantasy of absolute detachment. There's no God's eye view. There is only careful experimentation, clear thinking, and humility in the face of limits. The laws are real, but our access to them is always mediated through interaction. Once you accept that, the confusion fades, and something more powerful takes its place: clarity without illusion. This is why looking inside an atom feels so strange. It forces us to abandon the comforting belief that the universe is built to match our intuition. Instead, we discover that understanding is earned by discipline, not imagination, by precision, not storytelling, by accepting what the evidence allows, not what feels emotionally satisfying. And here's the final twist. When you truly absorb this lesson, it changes how you think about your own life. Your beliefs, your choices, the questions you keep asking, these are not neutral observations, they are interactions. They shape the outcomes you experience. Just as in physics, reality responds to how you engage with it. The atom teaches us this: reality is not revealed by demand, but by dialogue. If you want deeper truths, you must learn to ask better questions and be brave enough to accept answers that don't look the way you expected.